Okay, to start today, I'd like you to try this question. An unbiased coin is flipped 4 times. What's the probability of obtaining 1 head, 2 heads, and so on? Well, a good approach for this question is to draw a tree diagram. And I'm going to get 4 sets of branches. So I'm going to start it out by making it really wide. That's the first flip. Okay, second flip. Third flip. Fourth flip. Okay, on each of these branches, it's going to be a half. So I'm not going to write it on every single one, but you get the idea. And then if you multiply along the tree diagram, every single probability here and so on is going to be 1/16. So this will help us find out the answers that we need. Because for example, for 0 heads, it's going to be 1/16 because that would be here when I get 4 tails. For 4 heads, it's also going to be 1/16 because it's going to be here when I get 4 heads. But the other one's going to be a bit more complicated. So we need to maybe count and look for where we get 1, 2, and 3 heads. So this root here is going to, actually I just wrote 0 there, sorry, that should have been 4. 4 heads, 3 heads, 3, 2, 3, 2, 2, 1, 3, 2, 2, 1. It should be mirrored as well, the symmetry. 1 and 1. Yep, that looks pretty good. Okay, so now I can figure out probability of 1 head. Well, I've got 4 times that it happens. So it's going to be 4/16. And it's going to be the same for 3 heads. And that just leaves us for 2. 1, 2, 3, 4, 5, 6. So there we have it. This is one approach for how to work out these probabilities. And actually, what we've constructed here is a probability distribution. We could draw it as a little table. We could say that the random variable x is the number of heads obtained, and we could calculate these things. Okay, that was quite a lot of work. And what would happen if I changed it to 10 times? This is what would happen. That does not look good to use a tree diagram approach. And it turns out there's a quicker way. There's a much quicker way, in fact, and that's what we're going to look at today. We can find it in a different way, and we're going to be using what we did last lesson. So let's imagine a coin is flipped 8 times. How many ways are there of obtaining exactly 5 heads? Well, for this, one possibility would be heads, 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 tails, tails, tails. Okay, or maybe I'd get tails, 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 and then 5 heads, but I could have it all mixed up instead. But what we've returned to, essentially, is permutating 8 objects, so 8 factorial. However, it doesn't matter whether the heads, these are all the same, essentially, whether I get heads here and heads here. If I sort them round, I got the same thing. So I need to divide through by 5 factorial. This is what we've spoken about previously. And then I'm also going to divide through by 3 factorial because I've got 3 tails. And we'll see where we're going with this in a minute. Okay, but actually I'm finding out all the different ways that I could get 5 heads. Now I can actually work this one out by hand. It's going to be 8 times 7 times 6 times 5 factorial over 5 factorial, 3 factorial. The 5 factorials cancel, the 3 factorial is 6, it cancels with that, and I get a very nice answer of 56. Now what if I changed it and I did, I don't know, 4 flips and let's say 2 heads? Well, for this it would be 4 factorial because I've got heads, heads, tails, tails, or something like that, all the other combinations. And I divide by 2 factorial, 2 factorial. And what would I get? I'd get 4 times 3 times 2 over 4, and I would get 6. 6 possible ways, or 6 possible ways. So I can use the idea of permutations to work out the number of ways that this can happen, this thing that I'm interested in. I just have to also factor in the probability. And that's what we're going to look at today. So the advantage of the second method, I haven't done it yet, have I? Sorry. So if I want to work out the probability that I get 2 heads, right, it's getting a bit carried away. That is going to equal, well, there are 6 ways that I can get 2 heads, but then I'm going to need to multiply like along the tree diagram. So I've worked out the number of ways, but then I need to multiply by a half, then a half, then a half, then a half to get the probability for one part of the tree diagram. So it's going to be 6 times a half squared for all the heads, and then a half squared for all the tails. And yes, I know that I could have just done half to the power of 4, but I'm just distinguishing heads and tails for the moment. And that would again give me 6 over 16. And I could do the same for the other ones. If I wanted to do the probability of 3 heads, okay, let's write this out in full now. Well, it would be 4 factorial, because there's 4 things that I'm arranging, divided by 3 factorial, because there are 3 heads going on. I could even throw in a 1 factorial if I wanted to make it, because you'll see why in a bit. And then I would multiply by a half to the power 3 for the heads and a half for the tails. And again, we would get that answer. It would be 4 over 16. So I'm hoping I've convinced you of how great this is. We don't want a tree diagram. We can just use the idea of permutations and the fact that we essentially have a tree diagram. The tree diagram is there in our mind. This is us multiplying along the branches. This is us finding out the number of branches that are the same. Okay, and this is why it's advantageous. So a fair coin's thrown 10 times, find the probability of getting 3 heads. Well, right, so I want to know, right, probability of getting 3 heads, oh sorry, that it's fair. Well, that's going to be, one possibility would be heads, 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 and then 7 tails. Okay, and the probability of this specific one would be half to the power 3 times half to the power of 7. But then if I think about all the ways this could permutate, it would be 10 factorial, because there's 10 things, divided by 3 factorial, 7 factorial. And check that out, I've worked it out just with a single line. Let's keep going. Why stop there? What if it was biased? What if now the probability of getting a head was 0.7? Find the probability of getting 3 heads. Well, this time, for my heads, 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 it's going to be 0.7 to the power of 3 when I multiply along the tree diagram. And the probability of getting tails is therefore going to be 0.3. And it's going to be 0.3 to the power of 7. But that's just for that one single branch. I then again need to multiply by this 10 factorial over 3 factorial, 7 factorial to take into account all the branches. So we don't just have to deal with fair coins. We started out with that. We can deal with biased coins. Let's keep going. What if I change the probability from 0.7 to a more general one, P? Okay, Still, if we look at this one here, the probability of getting that exact combination, or permutation I should say, is going to be p to the power 3. Now, what am I going to do to get the probability of getting tails? I know that the probability of getting either of them is going to be 1, and actually that gives me my answer. It's going to be 1 minus p to the 7. By the way, you should be trying this as well, like, and just working along with me, like pause the video and when I start each example. Okay, 3 factorials, 7 factorials. So now we can deal with 10 throws for a general probability of getting heads on it, and we can find the probability of getting 3 heads. All right, let's forget 10 times. What about if it was n times? What would that be? Well, now this is getting a bit more complicated now. Okay, so I'm still interested in getting 3 heads. So it's going to be p to the 3. But this time, I've got heads, 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 and then all the rest are tails. So I know that I'm doing it n times. I know that there are 3 heads. So how many tails are there? Well, it's going to be n minus 3. So I'm going to times by 1 minus p to the n minus 3. And then how many things am I arranging? N of them. So it's n factorial. And then I want to get 3 heads. How many are left over? N minus 3 factorial. Okay, well, this is stepped up from that first question, but it hopefully all makes sense. And then I think this is the final one. Whew. What if I don't want just 3 heads, but I want x heads? What's that going to be? Well, for this, it's going to be, let's write some of them down. Okay, I've got x amount of these. I've got n in total. So it's going to be the probability of getting heads to the power of x. And then the probability of getting tails is going to be 1 minus p. How many am I going to have? Well, if I've got n in total and x over here, this is going to be n minus x, which goes there. And finally, we've got n things that we're permutating. I'm permutating x heads, and the rest of them is then n minus x factorial. And that is a general probability for this situation, which we'll now expand on. So we've ended up here, and I just want to remind you where we've come from. We started out just trying to find the probability of when I flip a coin 4 times of getting 3 heads. And we can draw a tree diagram. It's quite complicated. And then I said, well, what would happen if you had it to do it 10 times or something? And we built it up, we generalized, and we looked at the probability that if you flip a coin n times, the probability of getting a head is p. What's the probability of getting x heads? And it was this thing here. And I tried to explain bit by bit how we got to that. This is an example of our binomial distribution. So actually we've given the general formula for it. We just need to say a bit more about what it's about. So here goes. In general, I don't know why I've left such a gap there. In general, in a situation where you perform a series of trials and you either succeed or fail. So in this situation, getting heads was a success and getting tails was a failure. But you can apply it to anything. You could swap it around. So tails is getting a success, and then we just have to kind of alter the way we write it. But we just have to decide that one's a success and one's a failure. Then the probability of a success is p, and the probability that there are x successes is actually this thing here that I've written down. I'm just going to write it. I'm just going to copy it across. And what we say is the probability, because I didn't mention that, but capital X is the random variable. So it's the probability that this random variable is equal to little x, that I get x successes. That is our answer. That's our binomial distribution. Now, it actually turns out that this thing here can be written as n CX. So that's just a shorthand notation for it. It means we do n factorial, we divide by x factorial, and then we do n minus x factorial. Okay, so you will see this come up. Sometimes this notation is also used for the same thing. Q, I've used Q here in this other bit, but it's absolutely fine to write it as 1 minus P. You see both, to be honest. Okay, this is the same thing as this. It's just written slightly differently. So 1 minus P is the probability of a failure. And what we then say is that this random variable follows a binomial distribution. It's sometimes written bin, sometimes written with a B, with n trials as such, and a probability of success P. So that is the binomial distribution. Now you might be thinking, why has it got anything to do with binomial? Well, binomial because it means two. That's what, like bicycle has two wheels. So we're getting a success and a failure. If you want to link it to the binomial distribution, then we can do that because we could actually do P plus Q to the power of n, and we could expand that using our knowledge of the binomial theorem. Sorry, that's what I was trying to link it to. We're trying to link it to the binomial theorem now. And for this, you get P to the n plus, actually, yeah, you tend to write it like that, and then you tend to write it, often you write it like this. You write it as n1 and then P to the n minus 1 Q plus, and so on, plus n2 P to the n minus 2 Q squared, all the way up to your last term, which would be Q to the n. I've just replaced A and B by P and Q here. And check it out, this thing here is the probability that I get n successes, all successes, because, yeah, that's what it is. And this one here is the probability that I get n minus 1 successes, and n minus 2 successes, and finally, if I get no successes, I just multiply all the probabilities of my failures together. So this is how it links to the binomial theorem. Okay, let's look at some examples just to get a feel for this more. Let's consider that x is the number of heads when a coin is tossed 20 times. We can model this with the binomial distribution. So each coin toss represents a trial. N is equal to 20. And the probability of success is going to be a half. And this is what we can write down. That x follows a binomial distribution with n equals 20 and p equals a half. What about the next one? X is the number of sixes when a die is thrown 10 times. Can you write down a binomial distribution for that? Well, for this, we've got 10 trials, n is 10. The probability of success is getting a 6, so it's 1/6. And we can write this down. The x follows a binomial distribution 10, 1/6. This is just shorthand to tell us how to deal with it. And even though you can get 1, 2, 3, 4, 5, or 6, we're only interested in if you get 6 or not 6. So there is still a failure and a success. It's just that a failure is now worth 5/6 probability. And what about this one? A particular test has a pass rate of 60%. X is the number of students who fail the test out of a class of 30. Can you write down a binomial distribution for that? Well, be careful. Well, first of all, we see that we've got n is 30 because there's 30 trials, but we're interested in the number of failures. So in this case, actually, the probability of success is failing the test. It's a bit, contradictory, but we define this P to be a success as such, but it could mean anything. It could be getting heads or a 6. It could be failing a test. So actually, P is 0.4, and then we can write down our distribution. That x follows a binomial distribution 30, 0.4. So it seems a bit strange, but hey, we can still use a binomial distribution in this way. So we've derived the binomial distribution, this formula above, which we can write in terms of factorials or as NCX, or even as this one in brackets. We've talked about how it links to the binomial theorem, and we understand that we've got success or failure, we've got number of trials, and we've got the probability of the success. Let's have a go at some examples. So what I'd like you to do is try them yourself and then watch my video for some tips and tricks on how to deal with these sorts of questions. Okay, so for this question, we've got the x follows a binomial distribution. That's what that little tilde actually means. I didn't talk about that really before, where we've got 8 trials, so n is equal to 8 and p is equal to 0.25. So if I want the probability that x equals 6, then I've got 6 successes, 1, 2, 3, 4, 5, 6, and 4 failures. There are 8 things that I'm permutating. 6 of them are repeated, the s's, and then the 2 f's need to be taken into account. And then for each single strand on my tree diagram, like single branch rather, I'm going to be multiplying by 0.256 times and 0.75 twice. So I can put that into my calculator and figure it out. And remember, I can use 8C6 to do that more quickly. Okay, and I get this fraction, but actually, typically, this will be a model for something. So we do give answers to 3 significant figures. So 3.845 times 10 to the minus 3. Which I will write as in normal form as 0.00385. Okay, I've got a little admission to make at this point. So you can do it this way, and I want you to understand the process for the binomial distribution. But actually, there's a function on your calculator that will do it much more quickly, and you can use that from now on. But please don't forget about this with the factorials and the tree diagram, like going on the tree diagram, because that's your understanding of this topic, not just learning how to use the calculator. But let's look at it. So if we look on our classworks calculator, there's actually this option here for distribution. You can either press 7 or you can press equals. And then here is this thing called binomial PD, and that's what you're after. And if you just want a single value, you can go to variable, and here we go. You can actually type in the value for x that you want and the value for n, and the calculator will just do all this work for you. 0.25, and we get that same answer as before. So 2 different ways of doing it. From now on, we'll use this method with the calculator. If I want the probability that x is greater than 5, then actually that's going to be the probability that x equals 6 or 7 or 8, and I'm going to end up adding these together. Okay, I could work them all out, or I could go back to my distribution and this time use the list function. So I'm interested in 6, 7, and 8. The same number of trials in P, and here we go. Now it only gives it to 2 significant figures here, but if I go onto it like this, I get the full thing. But I don't really want to be writing this down, so what I can actually do is the following. I can store it in the memory. So this stores it in memory A. And the next one, I can store in memory B. And then the final one, I can store in memory C. Okay, don't forget you've got lots of memory functions on your calculator. If I go back to computation, I can then add these together really quickly. Okay, this fraction, and then we have 0.00423. Brilliant. So we can now apply the binomial distribution, and we can do it using our class whiz calculator. Okay, next question. Have a go at it. So in this one, x follows a binomial distribution with 10 trials, and the probability is 0.4. Okay, let's work out the probability that x is 1. Same as before, let's get back to the distribution, 7, binomial PD. This time I'm just going to list it because I can do both questions in one go. Let's do 1 first and then 0, so I get the order correct. And now I've got 10 trials, 0.4, done. Okay, the first one is 0.0403. And then for x equals 0, it's going to be 0.00605. By the way, for this one, it's actually, because it's going to be 0 successes, it's going to be 10 failures, and the answer would just be 0.4 to the power 10. But our class whiz can do it just as easily. Okay, this is the new bit to the question, really. It's the probability that x is greater or equal to 2. Now, do you want to do 2 plus 3 plus 4 plus 5 all the way up to 10? The answer is no. What we can do is something a bit sneakier. If we think about it, then if we got all the ones from 2 up to 10, and we add the rest, so the ones that are going to be less than 2, then that's going to be all the possibilities. That must equal 1. Now this x less than 2 is exactly the same as x less than or equal to 1. They're the same thing because I can't have values in between. This is a discrete probability distribution. Didn't talk about that before actually, but there's a difference between continuous probability distributions where your random variable can take any value, and a discrete one where it only can take certain values. Binomial is an example of a discrete probability distribution. So I can rearrange this to 1 minus the probability that x is less than or equal to 1. Fantastic, because I've actually already figured this out. It's just these two added together from before. So if I go back to my calculator and I store them into my memory, whoops, that was not right. Sorry, store A and store B. Then I can do 1 minus A plus B. Of course, I could have just done 1 minus A minus B. It's the same thing. Now we have it 0.954. Okay, so the addition, the thing that this question brings about is the fact that you can now deal with greater or equal to situations. Next question. So now we've got a wordy question. We've got data from Brian Air. The probability of a flight arriving on time is estimated to be 0.9. And I'm going to use this as a model to make future predictions. So x is going to follow a binomial distribution, and I'm doing 4 flights, so there are 4 trials, and the probability of success is 0.9. I should probably define my random variable. X equals number of on-time flights. Okay, but once I've turned it into this situation, I've turned it into this mathematical problem away from the words. So for them to be on time for all 4 flights, it's going to be that x is equal to 4. And you can use your class whiz for this. Actually, we could just do the 0.9 to the power 4, because there's only one way that I can have success, 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 success. And in fact, that's equal to 0.6561. Don't forget, though, that this is a model, this is an estimate, so I should still round it to 3 significant figures. What's the probability that I arrive on time twice? Okay, for this, I would resort to get my class was. So x is equal to 2, 4 trials, 0.9, 0.0486. And finally, the probability I arrive on time at least one occasion, that's going to be greater or equal to 1. But I can use the same trick as before. It's going to be 1 minus the probability that x is less than 1. In this case, x equals 0. And actually, I don't need my classes for this, because if for 0 successes, it's going to be 4 failures. The only way it can happen is if I have 0.1 to the power 4. And that ends up being 0.9999. Now, arguably, we should then round it to 3 significant figures, so it's going to be 1.00, which I'm a bit uncomfortable with, because you're kind of saying the probability is 1 that I will arrive on time at least one occasion, when we know it's slightly less than 1. But if you write both of these, it can be seen where we got our answer from. Okay, one more question. This does bring in one other feature, so stick with it, have a go at it, and especially think about part B. So the number of free gifts that Jan receives in a week is denoted by X, and this is going to follow a binomial distribution. We've assumed that. There are 5 trials because she buys 5 packets each week, and the probability of getting a free gift within our natural crunch crisps is 30%, which I'm going to straight away change to a decimal, 0.3. And again, we've turned it more just into the maths, forget about the words. So the probability that X equals 2 oops, 5 trials, 0.3, 0.3087. Which I'm going to round to 0.309. Okay, now B. So now we're looking not just at 1 week where we know the probability, but the next 7 weeks, and we're interested in whether there are exactly 3 weeks in which Jan receives exactly 2 free gifts. This, in fact, is a binomial within a binomial. What we're interested in is the number of weeks when Jan receives 2 free gifts. This is going to follow a binomial distribution of 7 trials, because we're looking at 7 weeks. And the probability of her or him receiving 2 free gifts is going to be this 0.3087 from before. Notice I'm going back to the non-rounded value. So y equals number of weeks that Jan receives 2 free gifts. Okay, because then we're interested in the probability that, oops, I was about to write x, probability that y equals 3. And we can use this binomial distribution above. So we're interested in, although it says x, we're now using y little y this would be. So 3, there are 7 trials. We know that it happens 0.3087 of the time. And there we have it, the probability of there being 3 weeks when Jan receives exactly 2 gifts is going to be 0.235. Okay, good little set of questions on binomial that test your understanding. Can you use the formula we've used? Can you then put it into your calculator? Can you look at these questions with inequalities in? Can you look at wordy questions? Can you construct a binomial within a binomial? Hopefully you're happy with this. Well done.